A very good evening, everyone. A very warm welcome to MazeX 1.0 Workshop number 1. We are excited to have all of you here as we kick off this incredible journey into the world of Micromouse robotics. This workshop series is designed not just to teach, but to guide you step by step towards building, competing, and excelling. Today, you'll get a clear overview of what lies ahead, from the structure of the competition to what you can expect in the upcoming sessions. So, stay tuned, stay curious, and get ready to learn. Moving on, this event is designed to combine learning, innovation, and competition through robotics. It's a hands-on experience where you'll explore intelligent systems and develop practical technical skills. Throughout this series, you'll also improve your problematic skills while working in a collaborative environment. Overall, MazeX 1.0 is not just about building a robot. It's about gaining a real-world experience and learning how to think creatively. Now, let's take a moment to introduce the experts who will be joining with us today. We are honored to have our two amazing speakers, Mr. Shamal, who is an application engineer at Synopsys, and Mr. Kiran Gunathilaka, a third-year undergraduate in electronic and telecommunication engineering at University of Moratuwa, each bringing valuable knowledge and real-world experience into electronic and mechanical design. Their insights will be incredibly useful as you begin your Micromouse journey. So, let's begin with our first session on electronics and mechanical design. Our first speaker is Mr. Shamal, an application engineer at Synopsys. In this session, he will guide you through essential concepts such as power systems, motor driver circuits, component selection, and schematic reading. We'll also cover mechanical aspects, including cases options, sensor mounting, and best practices for assembly. So, without further ado, let's welcome Mr. Chamath.
Thank you, Shay. Hope my screen is visible to you. Hello, am I audible?
Yes, sir.
Okay. So I hope you can see my screen, right?
Yes.
Okay. So yeah, today we're gonna discuss about the foundations and components and how you can start building a Micromouse. So I think since you all are interested in building a Micromouse, so the Micromouse is a competition where we build small robot, we call it mice, that try to compete and solve a maze which has 16 by 16 grids, and we want to try like we want to do it as fast as possible. So the main objective of a Micromouse is it should be fast and compact, and also it should be fully autonomous. Fully autonomous means you can't interfere with the robot even through a wire or any wireless communication method while it is on the grid. Okay. So when we talking about electronic aspects, there are four major components or four major things that you need to consider. The very first thing is the brain. Usually in this kind of robots, we use a microcontroller as a brain. Then this robot should be aware about its surroundings. So we need to select some sensors that the robot can identify what are the objects around it and how he is moving and his presence. Apart from that, the robot should should be capable of moving. So usually we use motors and motor drivers to do that. At the same time, the robot should be powered, and it is mostly powered by batteries. And there are something that you need to consider about power and power regulators in this kind of application. So moving on to the microcontroller guide, I have listed some of the microcontrollers that are already available on the market and which are also very popular. So first one is Arduino based microcontrollers such as Arduino 328P, which is very common in Arduino Uno and Nano. At the same time, ESP32 and STM32 is also there for a comparison. So when we are comparing microcontrollers, the most advanced thing that we are looking for and the most dominant factor is the processor. So usually Arduino based microcontrollers are 8-bit microcontrollers. It has 8-bit processors, and we call the AVR architecture that the processor has built. Apart from that, the STM32 and ESP32 are based on 32-bit architecture. So they are actually very much capable of solving complex calculations and handling bigger numbers in much faster way. At the same time, microcontrollers have a clock speed, which we can think of how fast it can work. So usually 8-bit architecture microcontrollers are running on 16-bit megahertz, and STM32 are like, there are a couple of STM32 microcontrollers. So they are usually working in 72 megahertz. ESP32 is advised, like they're advertising it as 240 megahertz, but actually you don't need that much fast clock. At the same time, this clock will be fluctuate when the Wi-Fi is doing bigger work. And since we are trying to build some faster robots, and you are trying to work on high complex algorithms, you need to have a bigger RAM and also a bigger flash memory. And this Micromouse has like lot of sensors and motors, like they have 2 motors at least, and lot of sensors to incorporate. In such cases, we need to focus on how many GPIOs there. So usually Arduino Uno has 6 analog pins, at the same time 6 PWM pins. Others are also capable of having a lot of analog inputs, at the same time PWM output. So apart from that, there are some connectivity methods. Usually when we are working with sensors and all, we need to connect them through some digital communication. So there are UART, SPI, and I2C. All of these microcontrollers are having them. But especially ESP32 is having Wi-Fi and Bluetooth. It's a something bonus, but actually if you need Bluetooth, you can add it later as a Bluetooth module. So it is not that much think of that you need to discard other microcontrollers over ESP32. When we thinking about how to start this microcontrollers, like work on microcontrollers, Arduino are very beginner friendly, and nowadays ESP32 are very popular, and the community support is also there. And STM32 is at somewhat intermediate level, but since you all are undergraduates, I think you could manage that complexity. And the cost is also, you can find it in mid to high range in the 32-bit architecture when compared to the 8-bit Arduino based microcontrollers. Thinking about sensor guide, the main objective is to identify obstacle nearby, or else we call it following the walls. So we can do it in couple of ways. So you can use ultrasonic sensors, IR sensors, sharp IR sensors, and time of flight sensors. But we need to consider the reliability of these sensors and the precision and the response time. When comparing all of these things, I think ultrasonic sensors can't handle that kind of fast response. And the precision is also very off the chart. And not only that, even though you select the correct sensors, the positioning of the sensors and the angles are very crucial when you are designing a micromouse. And there are some other sensors such as wheel encoders, which will help you to identify how fast your motors are rotating or how much turns that your motor is rotated during a turn. So it will help you to do precise control in straight line at the same time, taking some sharp corners. There is a sensor called gyroscope. It will usually output the rotational velocities in multiple different axes. So you can find like 3 axis gyroscope, and they will help you to, like, if you incorporate some algorithms, you can get the heading angle of your robot. So in this kind of maze, there are some segment that you could identify. Okay, now the robot need to go straight. So in that case, you don't need to scan the walls again and again. You can use this wheel encoders and gyroscope to faster your movements. Like once you identified any sharp straight um, segment, your robot can go very fast. So using these sensors will be come in handy to secure your scores. Apart from that, when you are developing this kind of robot, you can't make it right in the first time, right? So in that case, you need to interact with the robot while you are developing algorithms, while you are adding some sensors, while you are tuning the robot. So in that case, usually OLED displays, buttons, LEDs, buzzers, and Bluetooth sensors are very handy. Take it like that. Let's say you are working on your algorithm. So you are working on how your robot should move in some junctions. So in that case, you need to check how your robot is reading these walls and how it identified the um, current sensor inputs. So in that case, having a OLED or LEDs could helpful that you can use them to get some insight on what actually happens in the sensors right now. And also, let's say you are tuning some algorithms called PID or some kind of filters. In that cases as well, you can print the current values. At the same time, using buttons, you can change each of these values while the robot is on the grid. I'm talking about when you are developing your robot, not on the competition day. Apart from that, some sensors need to be calibrated in some changes in the environment. Let's say you have tuned your robot in your home. So the light condition of your home would be affected to the IR sensors. Now you are in the competition day and it's some indoor auditorium, let's say. In that case as well, the light condition has been changed. Now your sensor readings would be slightly different. In that case, you need to calibrate your sensors. And also the gyroscope need to be calibrated. And in most of these kind of Micromouse competition, there is 2 attempts. The one is your mouse should be scan the grid, and by scanning it, it will go here and there. It will take some wrong turns, and somehow eventually it will end up in the middle. But once it is there, it will resolve all these paths that he has already traveled, and he will get the shortest and fastest path. Then you need to move your robot into the fast mode. Then again, you need to place your robot in the first place, starting point, and it will be going through the shortest path. So in that case as well, to switch these modes, you need to have buttons. Uh, in this kind of robotic algorithm competitions, selecting a correct motor is very crucial. There are a lot of motors available out there, which is also applicable for Micromouse. You can find brushed DC motors without gears, At the same time, you can find brushed DC motors with gears. And also there is some motors called coilless DC motors. Coilless DC motors are similar to brush DC motors, but you might know there is a iron core in these brush DC motors, but the coilless DC motors doesn't have that. So it is little bit less in weight. So it could be some advantages when you are developing your micromouse. And also there are brushless DC motors, which is not much similar to DC motors. So you need to separately incorporate some controllers, which are very different how these DC motors are work. But these brushless DC motors are also in like they can also turn very fast. At the same time, you don't need to have separate encoders. You can get the encode output from itself. At the same time, it can handle higher torques as well. But I would suggest, since you guys are very new in this kind of experiment competitions, I would say going with gear DC motors are a good choice. So gear reduction system will be helpful to have a steady and higher torque to your micromouse. Talking about encoders, there are two types of encoders based on how they sense the encoding. So there are optical encoders and Hall effect encoders. And you need to think about how much resolution are there in your encoders. Apart from that, there are some other type of encoders, which is absolute encoders. I don't think it will suitable for this kind of application. So you are basically you would basically find incremental encoders in this kind of DC motors. And mostly Hall effect sensors are very popular. Now you have selected your motor. Then you need to select motor driver that is capable of handling this kind of motors uh, at different level of speeds, and um, the motor driver will help to give the necessary power to your motor. So when you are selecting a motor, there will be a specification that called continuous current requirement. So when the motor is running continuously, there will be a required amount of current that is mentioned by continuous current. And also there is a specification called stall current, which means when if your robot stopped at somewhere but still motor is running, or else someone is trying to stop the motor, so it will draw a lot of current. So your motor driver should capable of even providing such current in case of this kind of accident. Let's say you are tuning your robot, but it somehow hit on a wall and still the motors are running. But in case your motor drivers aren't capable of giving such kind of current, the motor driver would fail and it could burn out. Also, you should have a clear idea on voltage ranges. So there are some motors which are operated in 6 volt, and some of them are in 12 volts as well. And these motor drivers should capable of handling thermal management. Like they got to become very heat during this when you are developing the micromouse. Usually, like the competition won't take more than 10 minutes or so. But when you are developing these algorithms and all, you need to run it hourly to tune your values and such. So in that case as well, the thermal management of this motor driver should be capable of handling the heat. And for this kind of robots, we need to have at least 2 channels of DC motors. And also, you need to check which control interface this motor drivers support. There are 2 sets usually. One is PWM plus direction. So you can control the speed by PWM signal and the direction by another GPIO. And there are some other motor drivers which are capable of interface through serial or SPI interface. So in such cases, you need to have SPI ports or serial UART ports to communicate with that motor drivers. And also the PWM frequency of these motor drivers should support your microcontroller. So these values should be aligned with the microcontroller's PWM frequencies. And also, as I mentioned earlier, the thermal shutdown or like overcurrent protection should be something a bonus, or like you have to think about it in case of accidents. And because like the competition would be only like 10 to 20 minutes maximum, but when you are running it again and again, when you are dealing with your algorithms and all, the thermal management should be good. At the same time, if it heated a lot, thermal shutdown and overcurrent protection should be come in handy, because otherwise these electronics would be burned and you have to build it again. Okay. Now you need to have batteries and the power, because like now you have sensors and you have motors and the more drivers that are capable of running the motor. And also when you're selecting a battery, you need to focus on the motor driver voltage. That is that you have selected your motors according to that specification, and your battery should be capable of giving that stall current at least like 1.3 times of stall current. So when you are usually going for a battery, I would recommend going with LiPo batteries, and you have to check the C ratings or discharge rate. Usually 25C or 30C would be applicable. Because I said that you can use LiPo batteries is like they have higher energy density. The size and weight of the LiPo batteries are very less compared to the similar capacity and similar voltages in other type of batteries. But when you are working with LiPo batteries, you should never short circuit. At the same time, you should have a balanced charger, and otherwise you would the batteries could explode. So balanced chargers are somewhat expensive, and the LiPo batteries are also expensive. And apart from that, you need to do a power budget calculation, which is like you need to get the sensors when the sensors running, how much current is required, the microcontrollers, and all these electronic equipments in your robot, including motor drivers. So you need to calculate all of these things, and you need to calculate how long you need to run these robot, so that the battery capacity will be based on that. But usually we will get some higher capacity because we are focusing on developing this over and over. So we can't charge it again and again. So it should be somewhat higher battery capacity. Okay. Then you need to have less noise in your power channels. So you need to practice that you shouldn't have noises in your channels, especially sensors and microcontrollers. When you are designing a PCB or so, the grounds should be separated. Let's say the digital and digital controls, microcontrollers, and digital sensors, those should be separated. And the analog part would be taken as another segment, and the motor grounds. You have to separate each of these segments, power power zones, and should be connected only at a single point. It will help you to have less noise. Usually the analog part is the most critical in noise. So you need to incorporate inductors and decoupling capacitors to clean these noises, because power supply noises could change your outcome. Let's say sensor outputs and microcontroller outputs are heavily dependent on their power supply. So if you have noises in there, the sensor measurements and all, everything that depend on that logic could be changed. Okay. Apart from that, if you have not separated your power segments, usually this type of robots are going in different kind of accelerations, and it breaks sometimes, and sometimes it will take turns. So the motors will draw noisy and spiky current. So it will create some noises in the power supply. So you have to have separate voltage rails. Okay, and yeah, if you are willing to make a custom PCB, that would become handy because you can be flexible. Like you can design your own sensors, you can place them as you need, and you don't have to worry about these bulky modules. At the same time, you can use this both planes, and I think this PCB will helpful in building your chassis as well. But it has some complexities to deal with. So I would recommend, like, if you are very much beginner in this robotics, so you can use ECEDA, which is an online platform and easy tool that you can learn how you can custom PCBs, how you can design schematics, and how you can draw PCBs. And there are other tools as well, KiCad and EagleCAD, and also some professional level tools such as Altium and OCAD. So when you're designing custom PCBs, you have to think of sensor placement and the power management, and also you have to have testability and debuggability. What I mean by that is, like, sometimes you need to check is this power rail has the correct voltage. So in that case, if you are designing a PCB, you should have test points. And also I said, like, it's better to have a Bluetooth module to debug while robot is moving. So in that case, you can plug a Bluetooth module, but it is not okay when you are place your robot in the grid on a competition day, because you can't have any wireless communication. So in that case, it should be plug and play. And also, if you are working with STM32, you should have a place where you can plug your debug probes. So ST-Link, there should be a port to plug your ST-Link. And also, you should need to do the routing correctly. Like you need to calculate these currents, and you need to have the power rails routing strategies. And also, you have to have thermal management in your PCBs, because like motor drivers and all are getting heat in every time. So in that kind of areas, you need to have thermal management. So when you are routing, you should start with your power rails, and you should calculate the current that can carry on these kind of width. Like you have to think of your trace width, and once you have routed all of these power rails, then you can work on the motor drivers and motor driver circuits. And also, since we are working on DC motors, there is something called back EMF. So in that case, you need to have a freewheel diodes. So it will help you to eliminate this back EMF. So we call it flyback protection. Then you need to work on the analog sensors, and after that, you can try out the I2C for this gyroscope. After that, you can work on the microcontroller and other communication things. When you are working on this kind of thing, you need to have decoupling capacitors, as I mentioned earlier. So smaller values such as 100 nanofarad, those should be have very much near to the power IC pins, and somewhat higher values like 1 microfarad could be in intermediate on the sensor rails. And also you should focus on ESD, because electrostatic discharge could damage your sensors and the microcontroller. So having TVS diode on the PCB would be something that you can work on electrostatic discharge. So that's all for the electronic stuff. But I have listed some of the reference you can refer. If you are thinking of this kind of competition, I think you would better see others' designs which are already available. So I have listed some of these references, and also uh, some of these examples are also from some alumni, so you can reach to them as well, and you can study these reference guides and then plan things ahead. Once you have correctly identified what you need to do, then you can start designing. So I think there is a Q&A that you can put your questions and I will answer it in the meanwhile. And I think it's time for the mechanical design. It's over to you, Kiran. Yeah, we can see some questions. Do we have to participate as teams of for the competition? So I think this information will be information about the competition will be shared in the group or the channel. And will it be harder to participate in this type of competition as a beginner? No, because as I mentioned earlier, what you have to do is you have to select the correct sensors, and then you can work on your robot. And if you are new to electronics, there are a lot of available resources nowadays. There are very resourceful YouTube channels, and also now these AI tools are also coming handy. And if you need to clear some doubts, you can search online or search in these kind of AI tools, or else you can reach any resource persons that could helpful. Like you can reach to me even. So there are a lot of guides that you can refer that when you are working on Micromouse. So I will share these links that I have put in the reference through the organizing committee. The next question, what is the better choice, ESP or STM? So it depends. If you are familiar with ESP already, I think you can work with the ESP. But if you don't have any expertise on ESP or STM, I would say you can try on STM as well, because it's very standard microcontroller, and it has also have all of these things apart from the Wi-Fi and Bluetooth, and those things are not necessary in this kind of application. So yeah, it's up to you. But if you are at least have some expertise on ESP, or if you are even familiar with ESP, so I think you can continue with that one. Mm, in STM, there are some development kits that you can buy. They have a board called Blue Pill, which is very beginner friendly, and there are some higher complex ones as well. So I think you can give it a try using the Blue Pill as well. What do you mean by having separate ground to minimize the noise bit? Okay, so I think I have explained it earlier. So when you are working on different type of electronics, let's say some of these sensors are analog and some of these sensors are digital, such as gyroscope and all. And the microcontroller is also digital, mostly considered as digital. And the motors are actually electrical, so electromagnetical equipment, let's say. So in that case, these we have to treat them separately. Let's say you have to route all this power and all separately. And usually we would say when we are working with electronics, we need to have common ground. But it's a best practice is to have this digital ground, like all of these digital things have one ground, all of these analog have another ground, like in common one, and you can connect them it at a one point. Apart from having here and there, let's say you are sharing ground from analog to digital in one place and sharing it from another place to the motors, that would create a lot of noises in your power supply. So these kind of noises could change your sensor readings. And I don't think it is very obvious that all of these faster robots are heavily depend on sensor readings and the decision that you're make by the microcontroller. So if they got any noises in their power supply, all of these logics could have been failed. Let's say there is a wall and the analog reading is very far off due to a motors are running at very high speed. The readings are very off the chart. So it could do some like, although you have written the correct code, the result would be not expected. Um, yeah, how we can tune PID of robot precisely. So usually there are some sequence of steps that you can follow. Usually you have to start with P, then tune the D, and in this kind of application you don't need to have I. So like using PD will be enough in this wall firing task. So usually motor drivers are, I would recommend DRV, and yeah, it's you can find it in like modular one as well. Also, if you are designing custom PCB, you can find it as well, like as IC. And but it depends on the motors that you have selected. So DRV has some specifications, and if your motors are aligning with those specifications, you can use that. Yeah, I will share the presentation with the organizing committee. They will share it with you. It's a common way to mount sensors. Usually, you can use female headers, and if you think it's not suitable, then you can go with some custom PCBs and have some through holes where you can solder them directly, even for the modular sensors. If not, you can directly have a custom PCB where you can solder the ICs of these motor drivers and all these sensors. You can like you can do it by like there are some services as well. We call it PCB assembly services. So yeah, it's one way you can do that. What is the best programming? So usually you can incorporate Arduino uh, programming for all of these microcontrollers I have explained. And I don't think assembly is a better thing to do because it's like I don't think you don't have to um, handle that kind of complexity or the assemblies too. It's a overkill. Like you don't need to have assembly in this kind of computers. It's mostly C++. So I think that would be enough. Simulation. Yeah, there are a lot of simulation platforms like Vbots and Gazebo, and there are a lot of simulation platforms, and you can start working on that as well. I think a lot of tutorials are there, and I think Vbots is beginner friendly. Gazebo is somewhat complex. What is the best algorithm for this plot field, right hand, left hand? I can't quite say because it's depend on the grid and how the grid is designed. So yeah, that's one thing you can do is like you can have try to have these all of these algorithms and you can test it using your own grid and identify how it's gonna react. Um, yeah, I think I have answered the other question as well. Uh, there are no custom PCB manufacturers in Sri Lanka. So it's very cheap to buy it from China. Only the thing is the shipping cost is higher. So if you are working as a team, you can check with other teams or something to share the shipping. and order your PCBs together or something like that. In undergraduate projects, we did that. So you can share your shipping charges. How much would all these parts cost? Support contribution to purchases. Uh, I don't think there are support, but you could reach to some sponsors if you know some. Let's say if you have someone who is already working on technical industry and they are willing to sponsor your project, you can reach them. And I don't think that would cost much, but some of these sensors actually could be cost uh, some significant amount because of current economic crisis. Recommended RPM, yeah, it's something around 100 to 300. Any guide to implement and learn? Yeah, there are a lot of guides available. I think I will share it with you guys and you can refer them. Mm, yeah, even like when you're, let's say you are using Arduino, how the question is, how can we minimize our Micromouse by using microprocessors instead of using the entire board? So each of these development kits like Arduino Uno, it's the same IC and different form factor in Arduino Nano. And also it is very small in Arduino Mini as well. For the ESP as well, there are smaller packages. You can find it online. And STM as well. The blue pill is also very small. And yeah, the more suitable sensor type that actually you need to check. And it's these things are the key factors that your robot would stand out from others. So like you have to test it out and learn through your journey. So there are a lot of sensors such as IR sensors, sharp IR sensors, and time of flight sensors as well. So it's up to you to decide which one. And usually many of people are using IR sensors. And yeah. Stepper motors and input. So stepper motors are actually using to control precise movements, such as application in robot arms and all, 3D printers, CNC machines and all. So we are trying to build something moving fast. So in that aspect, I think stepper motors aren't that kind of suitable, but it's very precise in movement. So if you can you can control it precisely, but I think for this kind of application, usually encoders, like gear motors with encoders are the most suitable. The dimension of the Micromouse would be informed by the organizing committee. And brushed DC motors, yeah, I think DRE mode drivers are better, but there are a lot of other options as well. I think that's all for now. Yeah, anything else? If not, I think there are some other mechanical session as well. Um, IR array doesn't need to be here. Like we are trying to follow a wall. So IR array is when we are trying to follow a line. So you said that use debug probes. So when you are using STM32, it's not like you can't simply plug it to your computer using USB. So there is some debugger dongle. We call it STM link. So it will plug through J-Link interface. So there are some at least 4 wires. So you need to have those 4 wires in your PCB so that you can, once you have soldered this STM, you need to program it. So you can't usually use a USB type B or type C cable. So that's why I said like you need to have debug probes. So you have to plug them, like it's a male header. So you can plug them using a wires to the ST link. Okay, I think that's all.
Thank you, Mr. Chamath. We would like to represent this token of appreciation to Mr. Chamath Shamal in recognition of his valuable contribution as a guest speaker at MazeX 1.0 Workshop 1. Your insights, knowledge, and time have truly inspired and guided all of us here today. We deeply appreciate your effort in sharing your expertise and supporting the initiative. So, a link will be shared to collect your attendance at the end of this session. So, make sure to be with us until the end. We'll now take a short 5-minute break. So, at this time, it is a time to reflect on what you have learned. Prepare any questions you might have for the next session. So, enjoy your short break. Welcome back, everyone. We now move on to our second session, continuing with electronics and mechanical design. Our next speaker is Mr. Kiran Gunathilaka, a third-year undergraduate in electronic and telecommunication engineering at the University of Moratuwa. In this session, he will dive deeper into topics such as power systems, motor drivers, ESD safety, chassis design, wheel mounting. Let's give him a warm welcome to Mr. Kiran Gunathilaka.
Okay, thank you for the introduction. Everyone can see my screen. I'm audible. Can you confirm?
Yes, Mr. Kiran, you're audible.
Then I will continue the mechanical design for the Micromouse robot. And maybe as far as I can assume, maybe most of you might be amateurs into the designing and competing in the Micromouse competitions. Usually, one of the aspects that most of the contestants and participants get good is the mechanical design of a Micromouse. So basically, I want to through this session, I will try to provide some intro into the basics of basic aspects you need to consider about the mechanical design by going through chassis design and sensor placement strategies and motor mounting and wheel configuration settings. So, as I previously said, usually the mechanical design is not much honestly speaking, not much required if you are a country like you don't have to do serious mechanical design like doing a fully custom weapons or creating custom wheels and getting uh, creating and manufacturing uh, custom verticals and so on. But so that being said, so I will continue my session considering by mentioning that complete beginners should focus on when they come to designing Micromouse for the first time, and maybe how a seasoned competitor or someone with an experience should focus on the mechanical design. As Chamath mentioned, there are mechanical competitions, but usually you have to provide you have to there are two types of Micromouse competitions, standard Micromouse competitions and half-size Micromouse competitions. Usually, there's so far there's haven't been held any half-size Micromouse competitions to this day in Sri Lanka, but uh, getting only favorite is there's I hope visual is not fixed. So yeah, and usually in standard Micromouse comparisons, as I previously mentioned, even any beginner, someone who is new to the entire Micromouse landscape can compete and even win the even become the champions if they if they have a little bit sense about the mechanical designs. Well, usually we have to dive very deep into the serious mechanical designs and do very serious simulations, mechanical simulations, when you usually compete in the competitions like those half-size micronized competitions because usually you might have already seen those videos in the YouTube videos as well. In those competitions, the mouse travels immense as significant fields, and for in such cases, they have increased the grip and they have they are using suction fans to increase the grip of their increments. So that also those stuff are considered to be mechanical design related designs, and that I think for complete beginner who is going to participate for the academic conditions like usually in this Sri Lanka. So if I am to come into the chassis design, there are a couple of stuff that you need to consider. So basically, one of the factors is the size. Uh, so as you already might be familiar with, the standard Micromouse competition cell size is 180 millimeters. So that means 18 by 18 centimeter cell is considered as one cell for the standard Micromouse maze. So in that maze, let's say if you but the size of your the size of your robot determines the manuality inside the maze, how you can take turns, how you can do diagonal traversing, and yeah, and also, for example, as you can see in this image, usually most for example, there are two methods of taking turns for Micromouse robot. One is like in place turn, so this turn left, turn right, the images depicted here. Sorry, images depicted examples for such in place turns. Usually, there's a impact pivot turns also. These types of turns can be done using any kind of tool like you know, if your microchips can be placed inside the cell, then we can uh, is give me a minute. Can you confirm? So, better now?
Mr. Kiran, the audio is still not very clear.
Okay. Um, can someone confirm?
It's still not a bit clear.
Yeah, I think it's the issue with my network. Give me a minute. I show my face and my screen is visible to all of you. So basically, uh, when uh, so, when the contestant's approach is to use a robot that use only instance, that was main chance. He what type of approach does not require special consideration into the size of the robot. So, for example, if there's some like 3 to 3 centimeters, that's 3 centimeters available from the both side of the robots, both side of the robot to the like, basically if the robot is like below 2 centimeters, where it can easily traverse to any point of the maze. The contestant's approach is to use this in place stance or these in pivot stance. But let's say someone you as to not have observed in maybe like tutorials or maybe like experienced firsthand in the competitors. Some contestants have the ability to do small tasks. They are not turning completely inside in a single cell. They are doing that turn while forward. So in such case, the size matters a lot. For example, from my own experience, my first Micromouse product design, our Micromouse, it can be completely using the in place, the so-called in place terms. But when you change the control to use these fluid sense, and no matter how much we feed the parameters and tune the parameters and the algorithm and velocity profiles, uh, so, correct champion don't twice. But there's search and so 12 centimeters. The how much harder we try and how much sensors we add to our work detection for the founder for the we did not run it because because of the price, sensing size was too much high for performance adoption. And So, see, the other factor is so it's also for beginner. If you come if you have to screen for the first time, you don't have any case you don't have to actually first plan and I'm going to larger level just the uh, so that's the real cultivation. Most of the beginners that have seen in the UK are using two configurations. And some system contestants use phone configuration, but that comes at the cost of doing completely uh, custom comparison, and I will go into them in the next slides. Um, and doing chassis design, you have to initially design and initially consider the fact of what type of configuration you want to approach. Uh, the ground is usually trying to design your own. Uh, you consider on the ground, instrument can after the hazards and mistakes you might encounter processes. For example, say if you did not calculate uh, your base heights and everything with the automatic customers will not customers will not completely accepted. So the trial stage is must uh, and the service flexibility trying to usually I have seen that like when organizer participating in campaigns and when we are organizing committees, usually some contestants place their batteries for the usual batteries. The batteries then inside there. So batteries batteries described it's not functioning properly. Uh, and like sometimes have some stuff and they plastic. But we can't but we come in handy competitions and also during development. So to could increase the development time. So, some of you have some from control, especially in such cases, we have to send the and in case of but let's say if the company should consider this factor of serviceability, then they can by controlling that if they consider another should forget when the design Micromouse robot is the sensor wheel-based distance. So usually, it's like mentioned then like from my experience, so when you place the front sensors so close to the uh, for example, this image has this is the windows of the rubber hammer. Sensing of sensors that have been used to protect are used. They it's very hard for the Scenario they are using clearly algorithm clearly algorithm correcting its course and try to read those ways from the center of the walls. But when the sources way goes to the wheels, what happens is no matter how much tuning we do, uh, there's always still a little bit uh, I but for sure, it's three levels. Some students said, increasing distance between elements and placement of the detection sensors can increase the smoothness of the smoothness of the relay. And it can
Excuse me, Mr. Kiran, your voice is still not clear.
okay. Mm, okay. Maybe can that's why I'm not helping transition from my editing mode to the yeah.
Hello, sorry for the technical difficulty, and I hope now the issue is fixed now. Can anyone confirm again?
Yes, Mr. Kiran, now it's fine.
Okay, so I'll quickly go through the considerations mentioned here. So basically, the size. So if you need to take smoother turns and diagonal runs, usually you need to have a smaller robot, smaller Micromouse robot, because as I mentioned, no matter how much tuning algorithm tweaks you do in your higher layers in your code base, you cannot do those perform those precise movements with an larger micro mouse. Usually if your mouse is below 10 centimeters, by 10 centimeter and usually width of your mouse is below 10 centimeters, you might yeah, it can be considered as a good okayish design for performing those actions with good profiled good good algorithm and good code base. And the wheel config is basically whether you are going with two wheel approach or the four wheel approach. Depending on that, you have to decide what type of material and what type of motors, wheel hubs, and everything will change, and mounting positions of those change depending on what type of wheel configuration you are going to continue with. And the ground clearance is usually when you have like most of the beginner, but even during our first attempt we also did that mistake. We neglect the fact about ground clearance and assemble the robot assemble the robot. But when we trying to search for the matching caster wheel, we did not able to find one due to having too lower ground clearance than the existing casters available in the local market. And this by the serviceability fact, what I mentioned was you have to you like as we have seen in the competitions, and during even your development, usually the volatile parts like these motor controllers, sometimes even the motors, it's motors we can neglect because that's burning something like that is uh, completely undesirable effect. But like let's say motor controllers, batteries, and those type of stuff should be placed on a position that can be easily replaceable, because those type the people who have participated competitions might have experienced first-handedly. Those stuff goes up, blown out and goes out very easily. So placing those stuff in a easily replaceable position will decrease your development time drastically, all while you can, if some mishap happened during the competition time, you can like easily replace them if you have spare components available with you during the competition time. And the another major fact is that's usually not considered when development is the distance between the sensor and wheelbase. Usually the in that in the second micromouse depicted there, the wheelbase and the mouse, the wheelbase and the front wall detecting sensors are very close. And no matter how much tuning we done in the PID algorithms, and how much changes we did in the threshold parameters that were available in our control layers of our code base, there's always a slight wobble available, undesirable wobble available in our robot. We even had we had experienced that this wobble can be that like true precise. It should usually it should be that wobble can usually goes away with some considerably good PID tuning, but that by placing sensors and wheelbase to so close will make it harder for a contestant to do. Through some simulations, we had seen that by a robot with considerable distance between the wheel and the front detection sensors, and the uh, robot with a considerably low distance between the wheelbase and the sensors. The higher distance robot can be easily tunable, like with rough PID estimation is rough SPID gain values, we can easily tune the robot to follow a smooth path while for the same algorithm, while the robot with the smaller distance, lower distance between the wheelbase and the sensor robot does not have that smoother traversing, smoother path planning for the same algorithm, same code base. Can you move on to the next slide, please? So when after considering considering the previously mentioned specifications, you have a couple of options for designing a piece chassis. Usually, most contestants go with either these wearable as chassis or the PCB as chassis method. But I will go through each of them, mentioning the pros and cons of each of them. So basically, when using an acrylic based chassis, you usually have to like it's easy to develop, like developing a first prototype is easy, and and the design in the like the base also will be rigid. Like if you at least chose a like 2 millimeter acrylic board, the design will be sorry, if you chose an acrylic base, the rigidity of the structure is guaranteed. But the cons can be mentioned as the you need like compute like for usually those are laser cutted. For laser cutting, to get the drawing DXF files created, you need to have CAD knowledge usually, or SolidWorks or Onshape, or some knowledge in those area is required. And the other stuff is the acrylic based chassis are usually heavy compared to the other mentioned ones. Those are usually heavy, and they still need PCBs or other wearable based circuitry uh, compared to the other two options mentioned here. The other option is the easiest prototype one, the wearable as chassis method. So basically, you are using the I have included what's known as a wearable. That brown color ones are where some of you might have been familiar. So you can just this is completely a replacement for using a PCB instead. Sorry, using a wearable instead of the PCB. So basically, you are using the wearable and mounting all the sensors and do soldering at the bottom side of the wearable. So the sensors will act like basically you are creating a DIY PCB, and that will act as your Micromouse chassis. And it's the pros and cons of that can be mentioned as it's the easiest approach, and building such a Micromouse with the locally available component is very cheap. Like you can completely do completely develop such Micromouse within 10 to 15K maximum. But the cons of that are you need soldering experience. Like Like as I mentioned, you have to manually solder the components, and like do good wire handling between different levels, and you have to do such stuff. Yeah. And the other thing is, with these wearable chassis based method, is you have considerably low customizability. For example, let's say if you want to place a TOF sensor at a 45-degree angle, but as those uh, wearables have horizontal and vertical dots space to insert electronic components, usually you don't have the capability of adding custom angled placing custom angled sensors easily. Also, you for placing components, you have to do it in the incremental way, like the minimum snap distance you can place components in this wearable is the distance between distance between each of the holes. Like you cannot place components in between. So that's incorporated as the low customizability, and we have first-handedly have experienced that. And the other thing is the clean and most used method by usually the some contestant with some experience. But the thing with this is, usually this approach is very clean, and you have the highest customizability, and you can do a good job in like do custom place sensors and motors at precise locations, and can manufacture mounting positions for the motors sensors at exact locations with this approach. But the cons of this approach are, this is basically little bit expensive, and if you like expensiveness can also vary depending on whether you are going with modules approach or the uh, bare components placed on the PCB approach. For by that, what I mean was, if you chose to place the like the ESP32s that Chamath mentioned, and the IEMUs, uh, those component directly as modules on the PCB, then it will be less expensive, as most of the soldering can be done by yourself. But if you chose to go in a completely uh, component based, like components directly soldered into the PCB way, but that also have that approach also have uh, many benefits. But for beginner, that approach is not recommended, and that will also cost way beyond usual team's budget. Usually that will cost around $150 uh, with shipping. Usually closer maybe maybe higher, maybe it might exceed higher than that value. So usually that approach is also little bit expensive, even if you chose to go with the module based approach. And the other thing is, you need ECAD, or the electronic computer aided software knowledge. So basically LTM, if you have the access to LTM software, then you can use it. Or there are open source software called KiCad, and you can do a PCB design uh, to work as your chassis using that. So that is a that actually those facts cannot be considered completely as an con, because the main reason you are doing a Micromouse project or a project like this is to learn. So in when considering that fact, learning CAD, so you can do engage in learning those software by engage in such Micromouse project. And the other part is inflexible design. Let's say you have done a mistake in your schematic, or the you have wrong mounting hole diameters for your PCB, or wrong mounting hole placement in your PCB. In such case, the damage that you unlike the earlier methods I have mentioned, you cannot revert those mistakes after the PCB have arrived. You have to clearly design and go through multiple iterations of the design before sending it to the PCB fabrication fab houses or fabrication places. So that's the that's those are the pros and cons of the PCB chassis, PCB as chassis option. And the other very rare, but it's not much common, but approach is the 3D printed base as a chassis. So it's also a clean approach and relatively less expensive compared to the PCB chassis method. And it's also not that much time consuming compared to, because unlike PCB chassis method, usually there are not no good PCB fabrication houses available in Sri Lanka. You have to get them through foreign manufacturers. But when it comes to 3D printing, you can get considerably good 3D prints from within our country. So it's a clean and relatively less expensive method. But just like the acrylic one, it's little bit heavy, but not that heavy, because when printing with 3D printed base, you can like reduce the infill and other such parameters, and like reduce the weight, but not reduce but you have to be careful when adjusting those parameters, because that can reduce the strength of your Micromouse robot, and like it can easily break if you are not being careful. So you have to adjust between those uh, like do careful investigation and choose those parameters. And for that also you need CAD knowledge, as I previously mentioned. uh, can you move on to the next slide? And the other part is the motor mounting and wheel configurations. Usually for a beginner, this is like, if you chose to go with already off the shelf motor plus wheel plus encoder configuration, this is not a very big issue or very big issue. But let's say if you are as I mentioned, if you are experienced and experienced contestant, and you want to move on to going with custom four wheel configuration, then in that case this becomes a little bit complex, and you have to do many research, and it also becomes a little bit expensive uh, compared to the already available off the shelf encoder motor wheel combinations. So the the encoder motor wheel configuration, encoder motor wheel combination I have depicted here is the N21, the glorious combination used by most of the competitors all around the all the Micromouse competitions. So they come with two wheel configuration, like two wheel sizes, and that can, for a beginner team, this configuration will be might more than enough for them to compete and get a good running good working robot. So let's say, but if you are going with a custom wheel design approach, then in that case you have to consider about four components, basically wheels, motors, encoders, and wheel couplers. Wheel couplers are the ones that connect the motors with motor shafts with the wheels. So if you are going with completely custom design, in that case you have to like the wheel and motor design should be done together, and you cannot actually consider them as separate entities, because the motor, like let's say if you chose a motor from a AliExpress or some some foreign marketplace, and you design a wheel in house, like by yourself, by like 3D printing or curing silicone, something like that. And when you try to merge those two components, you see that shaft type and the shaft you made in the wheel does not compile, like they are not suitable with each other. So basically what I'm saying is, when designing a robot, when designing a micro custom wheelbase and mounting configuration for your micro mouse, you have to consider about all the facts and dimensions regarding the wheels, mounting positions, mounting types, like there are different type of shafts available for motors, uh, and also the other major factor is the encoders. Just like you, like from the N20 motors I have mentioned here, the in those cases the encoder is already placed in the end of the axle of the motor. But in a four-wheel configuration that you choose to do completely custom, you have to decide, you have to find a suitable encoder and place it in a plausible place, like yeah. So it's a completely different two ball games when it comes to designing, um, design getting off the shelf combination of motor wheel encoder, so and wheel, and design custom set of wheels and models, motor mount. uh, can you move on to the next slide? So uh, let's say, if so basically there are three wheel configurations available in my common micro mouses. One is two wheel, one caster, or the driving wheels, or the different, basically all the wheel configuration used in micro mouses are differential based. So basically they are using two wheels, and like the one side of wheels, not two wheels, the one side of the robot um, rotates rotates at the rotate in one direction, and the other side of the robot rotates in the sorry, basically in the differential configuration, the two sides of the robot are controlled by two different motors. And unlike like the another different wheel configuration is the Ackermann based one that is used in our uh, day-to-day vehicles, and the other one is like skid steer configuration. Those type of configuration are not used in micro mouses, and it usually used steering configuration is the differential wheel configuration. So in this case, these three wheel configurations can be used for your micromouse design. So basically, two wheel one caster method, your driving wheel couple is placed relatively at back, and one front uh, caster or a contact point is placed in front of the robot. Usually in this method is and the other method is, I will go through each of the method and then compare the pros and cons of this each method. And the other method is the two wheel two caster method. So basically in here, the motors and the wheels are placed at the center of the robot, and the two casters or the two contact points are placed at front and back of the micro mouse. So compared to the first mentioned wheel configuration, the placing the driving wheels at center make it easier for doing make it little bit easier, because the center of gravity is at the center, and casters are only there for support, and not like not for like uh, there's a considerably low effect from the casters to the second wheel configuration, but for the first wheel configuration, the casters effect somewhat marginally effect to the performance of the robot. And the easiest method will be the second method. And for yeah and but and for the and also the other wheel configuration mostly used is the four wheel configuration. And it's the one, if this is not I personally would not think this method will not suit for a complete beginner, but a somewhat experienced person. This can be a good initiative and good learning experience for them. And this design does not usually with this design you can uh, ignore the requirement of the casters, and that's a huge benefit, because usually casters effect to like casters introduce some type of undesirable friction to the robot, and that effect can be removed if you go with this four-wheeled micromouse approach. And it also increase the grip of the robot. And you can do like compared to the other two methods, using this method, the robot can reach up to higher speed, because yeah, relatively higher speed compared to the other method mentioned, without losing its stability. So can you move into the other slide? And when talking about the wheels, usually if you are taking off the shelf motors and wheels, those are usually those rubber wheels. And that will be enough for a beginner to get building a working robot. um, but if you chose to do a custom design, the rubber wheels would not be the perfect choice, because making custom wheels is not easy. As far Yeah, it's not comparatively easy compared to the other custom wheel choices I have mentioned. So the other wheels is silicon wheels. So basically, for the ones like for that half size micromouse competitions, usually contestants go with those silicon wheels. And even for a even for it's comparatively easy for us to create a custom wheel by like getting a UV light and get the solutions from market. And like we can with an if we have a good 3D printed mold, and we can cure a custom wheel using some using tutorials available in the internet. And the other approach is the 3D printed wheels. Mostly I have first-handedly experienced that most people go with if they are to do a full custom design, most people go with these 3D printed wheels. And usually they choose ABS material because of the strength and the durability of the robot. uh, and yeah, can you move on to the next slide? And when it comes to this fact also mainly involved with the custom designers, usually as I mentioned, beginners do not have to consider about such approach. For such design there are a lot of internet material available online, and they can go through them also. Even these materials I have uh, placed here are from popular sources available on internet. And in such custom wheelbase approach, usually what they are doing is they are mounting the mounting the wheels directly to a wheel mount that is mounted to the PCB chassis, and control the wheels using the motors using a gear mechanism. I You might it's not I'm not able right now, not able to clearly point out the geomechanisms. Usually that also have two different approaches, like people can choose to place like uh, chose to place the motor at center or mm, images I have placed here, the motors are placed at the centers, but some have also placing the motors at one end and control the control the wheels through a series of gear transformation mechanisms. Yeah, the other other method that I place is the N20 motors based approach, and they usually have this they does not have wheel couplers or anything. The wheel just basically fits straight directly into the wheel shaft, D shaft available in the N20 motor axle. And very they have very simple design, and you can, like, for a beginner it's very easy for them to get a working robot within couple of weeks, uh, if they go along with that approach. And can you move on to the next slide? And after the wheels, and I'm going to talk about the sensor placement. Basically, like you will get more information about these type of sensors that you can use. I will briefly introduce you to type of different sensors you can use. Basically, there are two type like for these are basically distance sensors. So there are two methods for detecting distances. One is time of flight, or the measuring the time the light to go out from the emitter and try, measure and receive, come back to the receiver, and measuring that time just like that usual ultrasonic sensors. It is using time that light it took to go to an obstacle and reflect it back, and calculate the distance from it to calculate the distance from the time to estimate the distance. The other method is using the reflected intensity. By like that method is little bit hard and compared to the using the T or TOF or the TOF sensors, because the TOF sensors are readily available in the market, and you can just get one out from the market and just hook into a microcontroller and get the sensor distance readings very quickly. But for the IR sensors, it's not the case. The IR sensors are measuring the reflected intensity, and the intensity, like use like as you might have encountered in A levels, using the inverse square law. The intensity differ like uh, intensity differs when we uh, intensity that's reflected to the on an obstacle differs when the obstacle distance differed from the varies from the emitter. So basically, it's measuring the intensity that's reflected back. But to get the sensors working, you have to do lots of calibration and alignment with the aligning the receiver with the emitter, and those stuff that are those calibration are much needed before getting a valid distance reading. And the other thing is, usually good IR emitter and receiver sensors are not available in Sri Lanka most of the time. If you are going with that approach, but the standard approach is actually the IR approach. But if you are going with that approach, you might have to get those from foreign markets and design your robot. And now coming back to the sensor placement, Usually you can, it differs from micromouse to micromouse. You can like do the design completely just using 3 sensors, or do the design using 4 sensors, 5 sensors, 6 sensors. That's up to that's completely up to you and your requirement and your experience level. Basically, in the first image, it's depicting a 3 TOF sensor based micromouse. So in there's I have if you closely observe, there's one TOF sensor in the front to detect the front wall distance, and there are two other TOF sensors available at the side of the micromouse to detect the side walls. So they will be used to uh, detect the walls and keep the mouse centered or at all times, and the front sensor will be used to detect the ahead upcoming walls at it front, and stop when it's necessary. uh, but the issue with that configuration is you do not have the luxury of detecting the wall corners. Like with that configuration, you don't have the ability to detect where the wall ends. Like you don't have the ability to predict where the wall ends. So that's the main con of the that sensor configuration. But compared to the other sensor configurations, it's much easier to build using just 3 to 4 IR sensors. The other second sensor configuration is relatively easy compared to the third sensor configuration I'm going to mention. In there, like these 1 and 5 sensors, with the 1 and the sensors indexed with 1 and 5 are used for detecting the side walls, just like the previous sensor placement. And the sensor indexed as 3 works similar to the uh, sensor in the front of the micromouse in the first image, and it's also used to detect the front walls. The another thing is this design has a two sensors to detect the corners of the upcoming walls. Like using 2 and 4 index sensors, they are using to predict where the wall ends. So so they can like easily perform smooth turns and do diagonal runs easily using those sensors. So basically, uh, they are they have placed two different dedicated sensors for predicting the walls ahead. Walls, not ahead. Predicting the walls at their sides. The other thing is the other configuration is the fourth one, and it's using just 4 IR sensors placed in different angles. Like the components from those angles, like after receiving a distance value, like after going through some analog filtering and averaging and doing multiple calculations, you get a distance reading, and using that distance readings and the angles they are placed on, they can get an reading on the reading on where the front walls and side walls are, using the components like sine and cos components of the walls. And like and you can perform you can also like go through some reference material also to identify what are the what might be the other pros of this method are. But for a beginner, I think the first approach will be the most easiest, and first or the second approach will be the most easiest for get a robot running. But mind you, you don't have to always go using the IR sensors, because even though also if one thing is these like calibrating and placing these sensors is hard, and the other thing is these IR sensors are susceptible to ambient light. So if the light conditions change from your calibrate, like from your development area to the competition area significantly, this can affect your robot's performance. That actually can be uh, fixed using proper calibration methods. But for a beginner, I think the most easier approach will be using these top sensors, so sharp IR sensors that just direct, like sharp IR sensors, so some uh, easy sensors, like easy distance measuring sensor approach, so you can get an working robot within couple of weeks. And also you can like, it doesn't like in even though in these images I have depicted that they are only IR sensors, you can use those TOF sensors. So such similar sensors placed in the same exact configurations, and they doesn't always have to be IR sensors. They are here just for the um, indication. Can you move on to the next slide? And the when doing the sensor placement, key variables you have to consider if you are using that IR approach. This does not concern with the TOF based approach, but if you are moving with the IR approach, you have to consider about the angle of emission and angle of reception. Basically, when placing the IR emitter sensor and the IR's receiver sensor, you have to refer to their data sheets and identify the FOVs and FOVs and some similar parameters, and do proper calculations and researching, and you have to adjust the angles of those two sensors precisely, so you can get a maximum you can get a good read on the intensity of the reflected IR beam. And the other thing is, during alignment, you have to like consider the like for different voltage, like you have to like when doing the calibration, you have to make sure what distance from, what is the maximum distance from a wall you are trying to detect, like and also the other fact is height above the ground, the where the sensors are placed, and uh, left right symmetry. Basically, if you like as in the previous images, there are two dedicated sensors both in left side and the right side. If the right side, if they are not placed at exact symmetries at both sides, you might have to do corrections on the algorithm side, like from the algorithm side, and it can be less desirable, and it might introduce some issues along the way. So the first good thing to do is uh, adjust get a good height above, like design the robot to suit like defined height above the ground, and uh, place the IR sensors at perfect symmetry in the front of the robot. So those are some basics regarding the sensor placement for a robot. Though most of the facts I have gone through here are for usually for beginners, and for use for some experienced competitor or experienced Micromouse builder. You can go along with the tips I have given and go in the references that Chamath had mentioned, and develop a challenging robot in your upcoming uh, for your upcoming competitions. So from my end, that's it for the mechanical design, and I wish everyone all the best with your maze solving. Thank you.
Thank you, Mr. Kiran. So moving on, you can ask your questions by scanning the QR code displayed on the screen. This will take you directly to the Slido where you can submit your questions in real time.
Okay, someone had asked that what is the drawback if you use the ultrasonic sensor. So usually, if you might know, if you go into the data sheets, the minimum distance of the ultrasonic sensor is much considerably much larger. So for in the applications of the Micromouse, you need your sensor distance reading sensor should be able to detect smaller distances like uh, about 2 meter, like it's much better if you can detect above 1 centimeter, like closer to 1 centimeter distances. But you in even the most toffs here can, like the most common toff available can detect distance above 2 centimeters. The for ultrasonic sensors it's much larger, and that's one of the main reasons you cannot use the ultrasonic sensors. And the another one is the sampling rate. Like for your control loop, if you use a TOF sensor, as far as I remember, you can get an about uh, the you, you can get an reading for each 20 millisecond, as far as I remember, for the uh, commonly available TOF sensors. But with an ultrasonic sensors, you will not your you cannot you will not be able to get distance samples in that much of short duration. So basically low sampling rate and not being able to detect smaller distances is the major drawback of using ultrasonic sensors. You can you like you can get and work in robot, but it's not recommended. What's the ID best ID for coding? It depends. Like it depends on your experience. Like if you have, like, let's say, as Chamath mentioned, if you have experience with STM32, then you can use the STM32 Cube ID. And but if you are completely new beginner, then you can use the Arduino ID. But if I recommend using the Arduino framework inside platform. Maybe you can go through them. There's a platform called as a framework VS Code extension called Platform IO. You can use that along with Arduino framework to program the robot. Basically, that choice comes down boils down to your experience, how much experience you have. If you are a beginner, use Platform IO with Arduino framework. That's my recommendation. What's the best place for caster wheel if you use 3 wheels? Uh, okay. Wait a minute. Uh, what is the best place for? Sorry, what's best? Can we use sharp IR sensors? Yes, you can use sharp IR sensors, and I have seen many people using sharp IR sensors in the Micromouse robot. How much does it go to create a PCB chassis? Like I mentioned, if you are not going to embed the components in the in the PCB, like embed the MCU, motor controller ICs, and all the SMD components in the PCB, then it won't be that much expensive, but it will for you, if you design a two-layer PCB, it will only cost around uh, $4 to fabricate, but to the shipping will cost around $27, 27 or 30, above that margin. But if you group group up and group up with your pool up with your fellow teams or fellow batchmates and get couple of PCBs from the same fabrication place, you can reduce the PCB cost to maybe 10k, 10,000 rupees. Yeah. What do you think is best, sharp IR or custom IR? I think for a beginner, sharp IR approach be much better. But if you have experience and you like a challenge and you want to have a higher sampling rate and you like custom controllability, custom custom controllability and customization a lot, then you can use the custom IR emitter and receiver pairs. Easiest up and running approach will be the sharp IR method. Can we use frictionless pads instead of caster wheels in two-wheel? Yes, you can. I personally have approached that, but sometimes judges say that if they identify that as harmless to the maze, one of the judges had one time of the competition had mentioned us that using that frictionless pad approach we chose was can be harmful to the maze, and they have the ability to disqualify us if they have the ability to disqualify us considering that fact. So be careful when using that approach. If you have uh, proof of showing them that this will not damage the maze, then that's fine, I think. Basically you can if you are working on a Micromouse, which microcontroller you will select. If you have no experience, then I'd suggest ESP32 or Arduino based on. ESP32 will be much better because it has as it has onboard wireless interfaces like Wi-Fi and Bluetooth. You don't have to have external Bluetooth interfaces and so on. So you can use them as debugging easily. And the RAM and the ESP32s are dual cores. They have two cores, and compared to the most of the Arduino boards are Arduino based MCUs available. ESP will be the easiest, and but if you are an experienced one, I suggest going with an STM will be the better choice because you can actually learn something, and you can actually do a greater job with an STM32 is microcontroller. What is a widely used coalesce motor? Coalesce, maybe I'm not, I don't remember the product name, but there are, if you search it on like AliExpress or some marketplace with something like drone cordless motors. There are some cordless motors available, but encoder choice that I'm not much familiar. Yeah, you have to do your own research. But if you take the international competitions, they are usually using the good motors called uh, fall harbor motors, like fall harbor motors, and some good dedicated encoders for them. But they are much expensive and they are not actually callers. Yeah. Before building the mouse, can we simulate the mouse? If so, possible ways to simulate, like the Chamath mentioned, you can use the most beginner friendly simulator will be webots. There's no point of using gazebo if you are like this application does not require the usage of ROS, so you don't have to like move into gazebo or like such advanced simulator. But for a Micromouse, if there's not a dedicated simulation task, I'd suggest there's some simulator called Micromouse simulator that can simulate your algorithm. Like you just have to replace your module. I think next speakers will mention this stuff, but I think I don't remember the exact GitHub repo, but there's some simulator called MMS or MMS simulator or something like that that can simulate your maze solving algorithm and the maze solving algorithm. You can search it up, but it does not let you simulate your motor controlling methods, your velocity profiles or anything like that. You can use it to simulate your higher layer controlling plot, basically your path planning and maze solving algorithms, your flood fill algorithms and so on. You can use that simulator for that. But if you want to simulate the motors and everything, more sensor behavior and everything, it's much better if you go with the robots. Yeah, can we buy frictionless pads? uh, Frictionless pads, that I'm not familiar, but for I what we had done in Micromouse competition was we had 3D printed a pad to 3D printed a base to fit into our robot and at very low sloped curved contact points in the front and back, and we smooth it out using sandpapers, so that acted as an frictionless pads. So for buying components, what is the best trusted method for highly reliable components? uh, I can't actually promote locally available uh, shops, but there's you can like basically the most of the locally available like for a beginner robot, like we are mostly using the tronic.lk or this, do you know, or that there are a lot of tronic electronic shops available in Sri Lanka, and they have like um, mediately good, like considerably good components. But let's say if you are using that IR approach, then the IR sensors available in those in locally will not be good. Usually you have to like I haven't mentioned those in my slides, but they you will be, you refer to them in the next upcoming sessions. You can get good IR sensors and receivers and good motors from DigiKey or else DigiKey and such foreign marketplaces. I've seen some competitors use vacuum fans. Yes, yes, that's also as I previously mentioned. usage of vacuum fans is I haven't even seen a single Micromouse competitor that compete with such mouse in our local competitions. Usually, that requires a lot of research and lot of. It's also kind of little bit expensive with the available shipping methods for Sri Lanka. But yeah, those are usually that type of vacuum fans are usually used for increasing grip and used for that the previously mentioned half size micromouse competitions. Usually for the standard micromouses, it's not required to use those suction fans for increasing the grip. And you can like you can do it as an uh, learning experience, but yeah, you can do it and it will increase the speed, but it's considerably complex than we think. How do we create custom mold silicon wheels? uh, you can create custom silicon molds, just custom molded wheels using like you can like go through internet tutorials available in the internet. Basically you will 3D print and mold and 3D print a mold of wheel you want and get the chemical solution uh, for getting the silicon and use a UV light to cure them. I'm not able to like give a detailed information here, and as the time is also running out, you can refer to the many available online tutorials. In Sri Lanka, which companies are half full size? The standard size micromouse companies are the mostly available. As far as I have seen, there haven't been any full size, half size micromouse competitions in Sri Lanka. How do we create custom? How long does a mouse take to? Usually, let's say if you are use a two-wheeled micro mouse and you use only in place turn approach I mentioned earlier, then in that case, usually that differs from the maze layout to layout and the algorithms the competitors use. But usually uh, in such case, it can complete a maze around 1 minute and 20 seconds. But I have seen that during the previous robotics micromouse competitions that there were competitors that were able to complete maze within uh, 20, 20 to 30 seconds, as far as I remember, using that custom made four-wheel smaller micromouses, the ones I had which depicted placed in my slide. So that's possible, and also with an half size micromouse with an like suction fans, you can reduce the time and by you as you can have a greater speed, but it also require good algorithms for detecting and good sensors for getting distance measurements. You can go up to you can reduce up to uh, within 10 to 20 seconds, I think, to create the maze for trials. What is usually when we were creating mazes, we use KT boards. If that's what you're asking, to create maze for trials. I'm not aware whether there are pre-manufactured parts are available. For by my own experience, what we had used was we used KT boards, and there are KT boards available at different thicknesses, and we merged a couple of like two KT boards to get the usually the wall size. Standard wall thickness is 1.2 centimeters or 12 millimeters. Using KT boards and some non-gloss material, non-gloss black sticker as ground material, we used to create mazes for our trials. I think I have answered that question. What is the main difficulties in four-wheel mouse? As I had mentioned, the main difficulties is aligning, like creating durable gears, aligning aligning those gears with the motors and reducing wear and choosing proper materials and uh, pro- finding this separate encoders, motors, and like you cannot directly mount the uh, encoder to the motor end. You have to usually to get the proper reading, the uh, correct reading, you have to mount the encoder into one of the wheels that were available in the one side, like, so you have to choose an encoder and have to find a method to interface that to the wheel, and you have to find an coupling method, like in the end-to-end based approach I had mentioned, you can get an that has a D shaft based wheel coupling mechanism. Basically there's no any coupling mechanism. You insert the D shaft into the wheel and it will tightly fit into the motor axle, but that will not be the case for the uh, custom four-wheel configuration. So that's why I said it's not recommended for complete beginner. But if you have time and if you are aiming for the aiming for winning the competition, and you want a great standard Micromouse, and like maybe like you have aims for competing in international competition. If that's the case, even if you are a beginner and you have a time and you are up for a challenge, then I suggest you can go for a four-wheel design. It's actually good challenge and will be a great learning experience. To create the maze for trials, I have answered that. I have answered that also. I think I have answered every question. Uh, there's another. How we can correct if two motors are not working same if it's going on crook path when it's so basically that also happens, like when we are buying motors from a cheap marketplaces. The two both motors can be different. In such case, you have to adjust that using closed loop, like these stuff will be covered in the earlier sessions, later sessions. Usually you can correct that using getting the feedback from the feedback of the wheel rotation from the encoders, and implementing a closed loop to maintain a constant speed. So you can, like, basically if the motors are different, if the motors are not behaving in the same manner, you can correct that using through your code base, through your software, through your motor controlling code. You can do that. I think I had answered every question. If there are any other questions, anyone can personally reach out to me and I'm happy to answer any of your questions. Yeah.
Thank you, Mr. Kiran. We would like to present this token of appreciation to Mr. Kiran Gunathilaka in recognition of his valuable contribution as a guest speaker at MazeX 1.0 Workshop 1. Your insights, knowledge, and time have truly inspired and guided all of us today. We deeply appreciate your effort in sharing your expertise and supporting this initiative. A big thank you to both our speakers for those incredibly informative and engaging sessions. On behalf of everyone here, we truly appreciate your time, effort, and valuable knowledge. Make sure to follow our social media pages and reach out to us to get the latest updates. So before we wrap up, we'd like to capture this moment with all of you. Could everyone please turn on your cameras and switch on your virtual backgrounds for the group photo? We'll give you a few seconds to get ready. So let's pause for the photo for the countdown. 3, 2, 1. Thank you, everyone. So here's what's coming next in MazeX 1.0. In the upcoming sessions, we'll be focusing more on microcontrollers and how they work, how to program them, and how you can control your Micromouse. You'll learn how to connect sensors, process data, and make your robot move intelligently. So make sure to stay with us for the next sessions. It will be really important, especially if you are planning to compete. So make sure to fill out the attendance form that is sent to you as well. I repeat, make sure to fill the attendance form that is sent to you all as well. As we come to the end of today's workshop, we encourage all of you to stay connected and continue this journey with all of us. There's so much more coming your way in the upcoming sessions, and each one will build on what you have learned today. Whether you are here to compete or to learn, your consistency will make all the difference. Stay motivated, keep exploring, and we look forward to seeing you in the next session of MazeX 1.0. Thank you.